Hello, everyone. Today we're in this new webinar. We have Nicolas Gauquelin, our colleague from the RIANA consortium. He studied chemistry and material science at the University of Rennes in France and graduated with a master's in solid-state chemistry in 2005. He then shared a PhD between his university in Rennes and the Aachen institution in Germany on determining the anisotropy of diffusion for lanthanum nickelate single crystals, for which he graduated in 2010. And during this PhD period, he got in touch with the electron microscopy and moved to the Electron Microscopy Center in Canada at the McMaster University in Hamilton for a 3-year postdoctoral stay, and learned about electron energy loss spectrum spectroscopy and advanced aberration-corrected microscopy when dealing with complex oxides. Later, since 2013, he became a researcher at the EMAT at the University of Antwerp in Belgium, and his expertise lies in structure property relationship determination at interface in complex oxides, 2D materials, EELS study at the atomic scale on various materials, so on and so forth. In particular, for in situ measurements of phase transitions, heating, cooling, biasing, etc. In RIANA, as a scientist, as a junior scientist member, he advises researchers in techniques offered by the eDream network. So with this in mind, we would like to ask Nicolas to just start his presentation, which is titled From Atoms to Electronic Structure, a Practical Introduction to EDX and EELS in the Transmission Electron Microscopy. Thank you. Please, Nicolas.
Yeah, thank you, Katalin, for the kind introduction. So my name is Nicolas Gauquelin. I work in EMAT here in Antwerp in Belgium. And I'm gonna, over the 45 minutes to an hour, talk to you and introduce you actually to what can do EDX and EELS in the TM. So here's the outline of my talk. So I'll first introduce EDX, then discuss what are the advantages of EELS against EDX and what are the drawbacks. Then introduce EELS and then move on to some more applications related, and go into complex oxide superlattices and how you can actually learn information about those complex structures at the atomic scale from electron energy loss spectroscopy. So to start, every materials are at the center of so characterization is at the center of a paradigm between structure, processing, performance, and properties. And all materials, being it metals, ceramics, glass, plastics, and even more complicated samples are made of atoms. And actually, to look at those, you need to go into the different scales. And here you can see the scale of things. So here in the micron region, so for like red blood cells or tracks on a DVD, you're in the micro world. And then when we go into electron microscopy, we go into the nano world where we go down to the atomic level. So which microscope can you use actually to look at those different scales? Well, first of all, if you want to look into the down to the nanometer regime, you can do that with an optical microscope because the wavelength of the light is sufficient to actually to see features down to 400, 600 nanometers, so in that range. And then if you want to go deeper, go down to 10 nanometer, even more modern instruments can go down to the nanometer regime. You can use an SEM, a scanning electron microscope, as you see here on the picture. And then if you want to go further down, and look at atoms and crystalline lattice, you need actually an electron microscope. So here is the oldest member of EMAT that you see operating one of our oldest microscope. But with that electron microscope, you can do a lot of varied things. And one of them that I will introduce now is EDX. What is EDX? Well, EDX is when your electron beam is interacting with the matter. You actually have a lot of rays that are generated and that are produced through that interaction. And the two that are interesting for us right now are the continuum X-ray and the characteristic X-ray, which determines the elements that you see in the EDX spectrum. So to go more into details, here is how it practically is done in the TM. So you have a detector, which is usually a silicon drift detector, into a cryostat, and then you see here you have the sample, you have some detectors around the sample, and on those detectors, the X-rays are collected, and from their energies, from the spectrum, you can get actually maps such as the following, where here you see a superlattice between lanthanum calcium manganate and barium titanate. And this can be done quite routinely in modern microscopes. What is the EDX spectrum? Well, the spectrum that you get is actually based on two parts. So you have the continuum X-rays and the characteristic X-rays. The continuum X-rays is also called Bremsstrahlung, and it's a background radiation, and it must be subtracted for quantitative analysis. It's due to the scattering of the beam by the nucleus, like you see here, which is absorbed by the detector and a specimen at low energy. And this is not actually due to an ionization of your atom. On the other hand, the characteristic X-rays can be used for elemental identification and are more quantitative and are product of de-excitation. So basically, you excite an electron from its ground state to an excited state, and from that excitation and the return to the ground state, you produce some X-rays that are specific for each type of atom and follow electronic transitions electron rules. So more practically, you see here is the incident electron. It will knock out an electron from a deeper level. This will be replaced by the de-excitation of an electron from here to here, which will produce some X-rays, which we will have the energy of the difference between those two levels. So what can you do with that X-ray? As in synchrotrons, the characteristic X-rays are qualified by a certain nomenclature of the edges. So you have the L lines, the M lines, the K lines, depending of which shell it's coming from. And then alpha, beta, gamma depends on the number of shells that the higher orbital electron drop to fill the vacancy. And the N, so 1, 2, 3, or 4, 5, is a subshell that the higher orbital electron came from. So more specifically, here you see some energy as a function of Z, and then you see here so that's depending on the excitation energy, so that's for SEM, and here you can see the characteristic lines, K lines simulated for each element. So these positions for each element are known, and not all excitations are equally probable, as you see here, which means that different elements produce different amounts of X-rays, and the ratios between the family of lines of each element are known and don't change. So the peak overlaps are possible. As you see here, you have very close the cobalt L and the silver M edge, or here the copper K alpha and the carbon K alpha, and here I think it should be the oxygen K alpha. So, but in independent of that, you can actually collect those X-rays and get on the atomic scale a map such as here, where you can get the lead MH, the oxygen KH, the chlorine KH, the iron KH, the titanium KH, and see actually really nicely the chemical ordering of the iron and titanium atoms, like you see here, and that at the atomic level. Another example is from a lone work that I did a few years ago, where we looked at atomically engineered interfaces that yielded some very strong electrorestriction coefficient. So, which means that when the material was being excited by an electric field, it produced some mechanical deformation. And here, so it's erbium stabilized bismuth oxide and CGO, so gadolinium-doped ceria, that were grown as a superlattice on top of neodymium gallate. And you see here, we see very nicely the layers, and from the HADF intensity, you can get a guess of what is the thickness of each layer. So they are very thin, down to 3 monolayer. And you see that depending on the periodicity, you will have more or less signals and more or less defined layers. And that you can see very well into the EDX analysis that you see here. So here is when the periodicity is 4.8 nanometer, when the periodicity is 2.2 nanometer, and when the periodicity is down to 1.62 nanometer. And you see that the intermixing between the two layers, between the cerium gadolinium layer and erbium bismuth layer, is actually increasing as you reduce the periodicity, which you would expect from interdiffusion. And what is the effect of that? Well, what you see here from the calculations is that there is a competition between making interfaces and the intermixing. And when those are actually optimal, which is this point, the electrorestriction coefficient is maximum. Due to the fact that we have a distribution on the reorientation of the elastic dipoles within the heterostructures and without an electric field. And what you see here is the HADF intensity, and you see also from the HADF intensity and for the strain that the more the thinner the layer is, the more it becomes homogenized through the whole superlattice. So, well, can you get quantified results from EDX? So, like composition, yes, you can. Most modern softwares include tables of K-AB. So the K factors, which are from standards, which are theoretical, which are from remote standards. But what is important to know is that depending where the beam is hitting and where the EDX, the X-rays are detected, depending on the angle, you can have more or less error, and the error can go up to 100%. So these K factors are not constant and depend on specimen and on experimental parameters. So, as Katalin introduced you, I will talk about EELS. So what is EELS? Well, I asked ChatGPT to help me, and he came up with the following. So that electron energy loss spectroscopy is, so you have an EELS that generates electricity instead of the electron beam, and we measure the energy loss as it interacts with the sample. So you have here your beam source, which is the EEL that gives electricity. And then from the rastering of that electricity, you have an energy loss that is detected by the detector and get an EELS spectrum. Well, I don't think that's correct, so I will give you the correct answer. So when you have your electron beam that is interacting with the sample, you saw that we were producing X-rays, so these can be collected on the EDX detector, and then the electrons that interacted with the sample that lost energy can be collected into a magnetic through a magnetic field and dispersed by energy, and that's how you get the energy spectrum. And that energy spectrum can give you a lot of information about elemental identification, phase, bonding state, bond structure, optical information, plasmonics, phonons, and etc., which I will go more into details in the rest of the talk. So what are the main differences between EDX and EELS? Well, lots of people still do EDX because it's cheap, it has a simple detector, it's user-friendly, you can do automatic quantification, the shape is very simple and just determined by the instruments, but at the same time, you collect just on a small solid angle. Well, it's been increased in more modern instruments, but the efficiency is rather poor. On the other hand, EELS, you virtually collect all the signal. But the shape of the edge, like in XAS, is more complicated and determined by the excitation. So you see, as we have also better energy resolution in EELS, you can see here the difference between the oxygen K edge and the nickel L edge seen by EDX and EELS. So you see, we have a lot of more fine features that you see here that I will go more into details into the future. So what is EELS and how does it work? Well, the electrons are dispersed by energy through the Lorentz force because you have an electrostatic field in the magnetic prism, and the combination makes the use of the to construct a spectrometer, and then you have a higher deflection of slower electrons than faster electrons. So how does it work in practice? Here you see, so that's that's here the spectrometer with all the lenses inside the spectrometer, and then you get the EELS spectrum, which can give you actually an enlargement on the camera, and on the camera you get the following. So here is your zero loss peak, which you can integrate and get the following signal on your CCD. But by shifting the spectrum offset with a prism current, you can actually get a core loss signal, like here where you see the oxygen K edge and the manganese L edge. So what is the excitation process? The excitation process is can be in twofold. So in valence EELS, you have a joint density of state and the bond structure information and optical properties because you are exciting valence electrons into the continuum. On the other hand, for core loss EELS, which is higher energy and more similar to Xanes excitations, you excite core electrons into the continuum, and from that you get actually some local density of state, bonding information, valence state, and composition. But as you have in a scanning transmission electron microscope, you can scan the beam, and then what you do is that you integrate over Q, but you resolve it in space. So what you see here is our bond structure, our intensity of the energy loss spectrum, like I showed you before. And then what you can do is that you can raster your electron beam across the sample and get in each of those pixels an EELS spectrum, which will give you a three-dimensional data cube that you can cut in any in any direction and get actually atomic maps or locally resolved maps of your different edges. Here is the same. The nomenclature of the edges is slightly different than in the EDX. So here you see so that we have the electron state notation, where it's the principal quantum number, G is the quantum number, the angular momentum, and then the transition to unoccupied states can occur only when delta L is around 1 within the dipole regime. So what are the different regions that you can investigate with within your EELS spectrum? So here you see a typical EELS spectrum with your zero loss peak that's electrons that didn't lose energy. Here you have the plasmon peak, which I will go more into details in the future. And then here from 50 eV, you have the high loss or core loss EELS, where if you magnify it, you can see actually core loss edges corresponding to the ionization of the different atoms. So let's go through the energy scale. So first we have the elastically scattered electrons that are giving rise to that very intense zeros peak. Then if you look into the tail of that zeros peak, below 1 eV, you will have actually phonons, which are atomic vibrations. And nowadays, with more modern microscope, you can actually study those phonons with the electron microscope in EELS. So by having a good energy resolution, you can actually look even here at the interface between an aluminum nitride and the silicon substrate. And you see that we can actually follow the change of the phonons across the interface. And this can be actually also mapped. So you can see, you can take different energies, map those different peaks. And by looking at the distribution of that intensity, you can see that we have a very intense peak between 24 and 25 milli eV, corresponding to that interfacial phonon. Another example is that you can get some momentum resolution by actually having a slit where you will not only collect your direct beam, but also some more scattered beam at higher Qs. And like that, you can actually get some kind of phonon density of state, like I can show you here. You see, so you can reproduce the phonon density of state by EELS measurement, and it matches quite well with the theory. A more common regime used in EELS is the plasmonic regime, the plasmonic loss. A plasmon is an oscillation of the electrons, of the free electron gas around the positive cores, which gives rise to a plasmon loss. And you have also in that region interband and intraband transition. So how does the plasmon peak look? Well, you see, depending on which metal or which material you're looking at, you can see that even for the aluminum plasmon, you will have different energies and different shape of this plasmon peak due to the fact that the oscillation is different. These plasmons can be used actually to look at the plasmonic modes. So here you have a metal rod that you can excite, and by your electron beam, you can excite those plasmonic modes, those surface plasmons, which you see as these peaks. And by mapping those peaks, you can see the different modes of your plasmonic response. And this has been used a lot for nanoparticles, where when you have a particle size that is changing between 5 nanometer and 100 nanometer, you change a lot the wavelengths of the plasmonic excitation, and that can be measured in EELS and investigated. Interband transition and band gap, well, you can also see those inside the EELS spectrum. So here you can see, for example, the band gap. And the band gap, we can measure not only the direct band gap, but we can also measure the indirect band gap. The definition of those band gaps and the exact determination of their energy is a bit not that straightforward, but can be done with careful care. And what you can see here, you have a pi star peak here, like on graphene. And this pi star is actually due to an interband transition. What is an interband transition? Well, you have an incoming electron that is going inside the valence band. Your electron is excited into the conduction band, and this results in the bond in an energy difference, an energy loss of your electrons, which can be measured as in your EELS spectrum. So here is some work that we did on luminescence properties of materials through EELS. So here you see an emission spectrum. You see those different bands of emission, the charge transfer band. And when you see here, we have the EELS spectrum. So I reverted the energy scale to actually be able to convert it into wavelengths. And when you look at the same wavelengths, you can see that we can get in our EELS spectrum a similar signature as in the emission spectrum from that specific wavelengths. So what can we see also in the low loss spectroscopy? Well, what you can see here, for a thin specimen, you have only one plasmon. For a thick specimen, you can have multiple plasmons. And that's due to the fact that you increase the probability of plasmon excitation and multiple inelastic scattering events, which means multiple plasmons. And this is commonly used to actually determine the specimen thickness, where we will look at T over lambda by looking at the difference between the intensity under the zero loss peak and the intensity of the inelastically scattered electrons. Another regime, when you go further in energy, is the more common inner shell losses due to inelastic scattering or core loss. Just to give you an idea, these different regimes have different scattering angles and require different detector geometries to be investigated. So you see that here plasmons are very, very narrow in Q, whereas phonons are very extended. What kind of information can you get from this core loss regime? Well, you can get the following. You can get chemical quantum, you can get chemical concentration, electronic structure, and nearest neighbors through EXELFs, similar to EXAFs, which is less done because it requires a longer acquisition time. So core loss ionization edges, here you see the boron K edge, the carbon K edge, the nitrogen K edge, the oxygen K edge, and similar to X-rays, the position of the core ionization edge corresponds to the binding energy of the shell. So these edges have different shapes, like you see here for a K edge. Here is an L edge or an M edge, which will have very different features. And this is combined with a background and needs actually some very careful investigation. So for relative quantification, what we do usually is that we look at the atomic ratio of element A and B, and we determine it. And I is the integrated intensity under the edge, and sigma is the inelastic scattering cross-section, which is tabulated for each element, but depend a lot on the conditions of your experiment and on your instrument. So what is the origin of that fine structure, and why do we want to use monochromators in TEMs? Well, the excitation process, as I showed you, is the excitation of a core electron from an atom of the specimen by the fast incoming electrons. So this electron will be kicked in an unoccupied local density of state. And this electron, so the incoming electron, will lose some energy and get into the spectrometer. This will result with an excitation of that electron into the unoccupied density of state, which will give the experimental edge. One example is TiO2. So here you see we have the simple unit of titanium oxygen octaedra in our solid TiO2. If you would do the molecular orbital diagram of this octaedron, you will get the following energy levels. And what you can do is that you can look at the different occupation of those levels. And from those occupation of the levels in terms of energy, you can get actually the following unoccupied states distribution, which will give you the same as the shape of your EELS fine structure. That EELS fine structure can give us a lot of information, like valence. So here you see, for example, these are different manganese compounds, manganese oxides, going from manganese 4+, manganese 2+ to manganese 4+. And you see that the shape of the oxygen KH and the shape of the manganese LH is very different and can give us a very nice signature of the different valence state of our manganese. How does it work on the oxygen KH? So you see, so here are the different transitions that are possible, and from the different transitions that are possible, these will result in different peaks, and these peaks are due to hybridization of the oxygen 2p states with the manganese 3d states. So how can we measure those? Well, we use those with an aberration corrected stem EELS, where here you see the standard trajectory of the beam without the monochromator excited. When we excite the monochromator, we spread the incoming electrons by energy and select a specific energy, which will be used further down into the TEM. And like that, we can actually reduce our native energy resolution of energy spread of the electron beam, which is 1 eV, to 215 eV and even 100 millieV. So I see that I'm running late in time, so I think I will have to cut short.
No problem. You can continue. We're here.
Yeah. So a monochromator, what does it do? It actually gives you a much smaller energy spread of your electrons in your incoming beam, which means that you will have the reduction from 1 eV full width at half maximum, here that you see on the Schottky emitter, to around 100 millieV. And that gives you actually the way to visualize all the very fine features like you see here on that cobalt LH. And using this, we can actually go even more into details into understanding material at the atomic scale or at the local scale. By here, what you can see is that we simulated this cobalt LH for different environments and different valence states, and by combining those, we could identify what was the exact local state and distribution of crystal field splitting and type of cobalt 2+, cobalt 3+, and cobalt 4+ within our material. And like that, we could identify that we were having at the interface between this inclusion and the matrix some square planar coordinated cobalt 3+, which was giving rise to superconductivity. Another example is cathedrals can be cleaned. So you see that black dust that is coming from environmental pollution, and that can be removed with a laser, with a laser treatment. But this gives rise to some kind of yellowing of the stone. And with some collaborators from Paris. We investigated this a few years ago, where we looked at black crust particle and yellow gypsum particles, and by comparing irradiated model crust where we don't have the laser treatment and where we have the laser treatment, we could identify that what was happening is that you were having some ejected particles of iron oxide at the surface, and that this was giving rise actually to the yellow color due to the fact that we were having some very small nanosphere of magnetite. In a more modern microscope now, you can actually collect different regions of energy at the same time, and you can get on the newest development of Thermo Fisher, you can get even 5 regions of energy all at the same time. So you see, we can get fine structure of the potassium LH, the titanium LH, the oxygen KH, and the europium H all at the same time at very high energy resolution. And this can give us actually a very good idea about what is happening across that interface. One more example is for lithium battery material. What you can do is that you can look at the lithium KH, like you see here. So here you see the lithium KH very nicely in EELS. We see the fine structure, and by understanding that fine structure, we can actually understand what is the effect of that coating on the performance of the battery material. Another example coming from outer space. The dust in the space are processed silicate, and when they cool down, they result in some amorphous olivine, and that amorphous olivine is very often having iron present. And what we saw is that when crystallizing some amorphous olivine, we can actually see some very small particles that are crystallizing at a much, much lower temperature than the tabulated crystallization of olivine. And what you see here at 400 degrees is that we have some very small nanocrystals containing iron. And what we did is that we did EELS on those, and we could look at the silicon LH, the magnesium KH, by looking very carefully into the fine structure evolution as a function of temperature. We could see that from 400 to 700 degrees, we have actually an oxidation of the iron. And that is due to the fact that the iron is precipitating first as oxide. And what you see here very clearly is that when you compare the matrix to these crystallites that are forming at 400 degrees, you see a much higher iron content than in the matrix, due to the fact that these first particles that are crystallizing are iron rich. This was also interesting. As you see, we are using an electron beam on a material, and this electron beam can induce some damage inside the material. And this damage can actually change the mechanical properties of the material. So here, I will not go much into details into this work, but what you can see is that by doing EELS, at different incoming electrons, we could identify the region where the damage was minimized, because you have two different sort of damage. So at low voltage, you have an ionization damage, which is called radiolysis, whereas at higher energy, you knock on your electrons. This is knock-on damage. And by doing measurements in EELS, of what was happening when we were putting our electron beam on the sample, we could understand the threshold between those two and the interplay and their effect on the mechanical properties. So I will finish, maybe go very briefly through this by going through complex oxide superlattices. So as you see here is emergent phenomena oxide interfaces. So you all know the conductive LAO-STO interface. You know the suppression of magnetism when you put ferromagnet in interface with a superconductor. Well, you can look at those phenomena at the atomic scale. Here is another example where we looked at magnetic induction reversal. So we reverted the easy axis of magnetism from an A axis to a B axis just by changing the thickness of a buffer layer between our LSMO and our substrate. And so here is an atomic map with EELS, but more into details. We could understand what was happening and the thickness effect on the Curie temperature of the material by looking at hybridization and octahedral tilt. So here, the change of the BOB bond angle is changing the orbital overlap of your manganese and your oxygen 2p. And this can be seen by changing of the angle. So here is an image in annular bright field where we see the oxygen sublattice, and we could determine the angle and the change of the angle and the interface. So you see that you have some octahedral tilt present at the interface between your substrate and your film. And this can be actually revealed by EELS by looking at the difference between the buffered sample and the non-buffered sample, where you see that these states, so this peak corresponding to hybridization of the oxygen 2p with the manganese 3d orbitals, is actually strongly decreased in the first layers at the interface between the two materials. So I think in terms of time, I will switch all the other for you and go to the acknowledgements. So I will acknowledge my group, EMAT, and a previous European project is Team 3, which gave me some interesting materials and a lot of experience in providing transnational access that I'm using now for RIANA, and funding and collaborations, and you for your attention. And if you have any question, feel free to ask.
Thank you very much, Nicolas. It was a really interesting presentation. Let's see if we have questions from the audience. Please just let us know with your hand, or just write in the chat box. For the moment, there's no one. I will ask one short question, please. The chemical analysis, is there any limitation similar to EDX? I imagine, right?
Yes.
Okay.
Yes, there is limitations because so depending on the thickness of your sample, you will have pleural scattering, and that can be corrected. But as you have also a background, so the quantification through EELS can be done more precisely with modern softwares like the model-based fittings that we developed here at EMAT. But it's still something that requires a lot of work and that is quite difficult, because you also have to take into account electron channeling into effect. So depending if your material is on zone axis, is not on zone axis, you will have a different quantification. So
Right.
That needs to be carefully taken into account, and there have been a lot of work over the last decades on this.
I see. And the mapping resolution of the technique, approximately?
That depends on the edge.
Of course.
So the lower the energy of the edge, the more you have the localization of your electronic signal.
Right.
But for example, for the oxygen KH, the delocalization is around 2 angstrom.
Right. And when you were presenting about the plasma spectroscopy,
Yes.
for that,
Yes, for this, there
we
is a much
what's
larger delocalization because the delocalization is inversely proportional to the energy loss.
right. Okay.
So it's more into the few nanometer range.
Also, we have a comment from the
Yes.
audience, Sombun Chaya. They say at atomic level, at atomic resolution ELS mapping, can we see orbital density from spectrum imaging? My case working on square lattice. Thank you, Sombun.
Well, there was some work by Stéphane Leffler, and I've been involved in that in the past, where we tried to do orbital mapping.
Right.
And this can be done, but requires a lot of correlation with DFT and very specific conditions for the spectrometer.
Right.
But more modernly, it is easier to investigate for the phonons.
Okay. Any other questions from the audience, maybe? Don't be shy. You can also do it in audio mode. Turn on the camera if you want. Nothing more. I had another question also about the resolution, because this is I also work in a bit in analyzing nanoparticles, in particular by TM and of course EDS. EELS was a rather unknown technique for me, so
Yes.
very well explained. Thank you. It was about the quantitative aspect of the technique. So you said there can be some errors up to 100%, meaning what they can the technique could actually
Well,
give
that depends
false
on the
results.
edges, that depends on the elements, and that depends also on the so for example, also the detection limit and the so it's very case specific
Right.
in that sense.
Right.
But
Okay.
modern software can quite well give you a quantification down to 1% or 10%.
By the way, about the software, the modern software,
Yes.
are you currently using AI for this? Because it seems to me it could be a
There is a
very
lot of work on
yeah,
using AI in electron microscopy.
it could be a very useful tool.
And yes, yes. So there is a lot of work actually on that. So,
Okay,
but I'm not using it personally. I'm more of the traditional way,
I see.
using my expertise.
Of course, of course. It's always better to do it, but sometimes it's better to compare it just to see because sometimes the resolution of AI goes deeper.
Yes,
Anyway, it's always better to be open to anything available. So yeah.
of course we are.
Okay. So there's no other question in the audience. I would like to thank you again, of course, for this really thorough and comprehensive presentation and the technique, which for me, as I said, it was completely new. And
Well, I can talk to you about it for hours. So if you want, we can have a call
don't
with a
worry,
beer. And
I will call you after the after we finish the recording. So yeah, with no further ado, thank you again for the audience for being here. Thank you for the presentation, and we are looking forward for our next webinar, which will be announced soon. For the ones which are on vacation, enjoy your vacations. For the other ones, enjoy summer. Cheers and best wishes. Goodbye.